Well, thank you for the invite. Again, my name is Jimmy Bo. I'm the Global Program Manager uh, within GNW Electric for the CLIP Current Limiting Protector portfolio. We're going to be talking today about mitigating incremental short circuit fault levels in electrical systems. GNW Electric, I'll say, provides electrical solutions to strengthen the grid. And we are a global manufacturer of commercial electrical equipment to make the power grid more resilient and reliable. And in today's presentation, we're going to provide you with a better understanding of some traditional devices, traditional and modern, to reduce faults and increase reliability of critical infrastructure. So if I get your attention there to that picture to the right, what it shows is a fault in a manufacturing facility. It is a catastrophic event due to faulty insulation. You might ask, what is faulty insulation? Well, it's a breakdown on insulation due to a variety of reasons: faulty equipment, human error, pollution, and electrical overload. So I want you guys to be thinking throughout the presentation about those three questions to the left. Are you prepared? Is your system rated to prevent this? And how can I prevent this from happening? And the purpose of the presentation is for, hopefully for at the end, you will be able to favorably answer these questions. Next slide. So the grid is changing, right? The technological advances are driving the need for transformation. And there's ever increasing demand of reliable energy, and which is generating that for these systems to grow and accommodate that increased capacity, which then leads in proportion to higher fault current levels. And that leads to problems. What problems? Increased cost due to insulation breakdowns or faulty equipment, project delays due to downtime because of that faulty equipment, and in worst of cases, safety issues, which can all the way to loss of life during catastrophic events. So today you're going to learn, I'm going to talk to you about some traditional protection components to avoid those situations. And in some circumstances, those protection schemes or components are insufficient. So then Andrew will then dive into the newer methods, which includes current limiting devices. Next slide. So why are the fault levels increasing? Well, because of this historical power revolution that we're going through, which is driving energy demand to, again, historical levels. Leading the way on that is data centers in markets such as cloud computing, data mining, analytics, and above all, AI. We see it everywhere. We see it in the news, investments, startups, left and right. We're looking for ways to implement AI at work, in our daily lives. Nobody wants to be left behind, right? So all that AI craze is generating a lot of energy demand. But it's not the only driver. We have transportation and all the renewables, right? All this two-way flow of energy, which honestly the grid was never designed to manage or handle, right? We have larger transformers, again, power grid expansion to meet that increase in demand, all increasing current fault levels. Next slide, please. So now let's talk about the traditional protection used to counter these fault levels in your systems. One of them being fuses, which we are all very familiar with. They quickly interrupt and limit the flow of current, and they do so by limiting magnitude and the duration of the fault. Two examples of those are backup fuses, which, as the word states, they back up another fuse, and they're used to handle very high fault current levels. And another one is the current limiting fuse that can also be standalone, and by definition, they're current limiting, so they limit current to under half electrical cycle. The pros is that they're widely available, they're inexpensive, and they're very low maintenance. But the cons is that they need replacement every single time that there's an operation, right? They're expended. They have limited availability at higher ratings. Most of these are rated under 1,000 amps of continuous current. And honestly, in a lot of situations, they just are not enough. Just like fuses, they are also limited in flexibility constrained by their TCCs, or time current characteristics. We also call them melting curves. Next slide, please. Another set of traditional protection components are reactors. They are passive and continuously limit the flow of current. It's very important to emphasize that on this solution, you limit the fault, but not the duration of the clearing time of such fault. It is the operation or the application is that you are introducing an impedance into your system. Two examples of these are the current limiting reactors for three-phase protection. And the second one is the neutral ground reactor that, as the name states, it's a limiting fault from line to ground. Pros, widely available as well. They manage higher ratings than your regular fuses, and again, low maintenance. The con is that they're very large in size. So if you have constraint in real estate, this might not be the solution for that application. Poor power quality due to the impedance that they do introduce some voltage sags into your power system. And again, because of the impedance, you have a low power efficiency, right? So you're gonna incur into power losses into your system. Next slide, please. And this one slide is to just give you perspective into the two different traditional solutions that I've just presented. To the left, a current limiting reactor. As you can see, it could be few stories high. That's in a substation. And versus the current limiting fuse that could be in the realm of 2 feet wide by 5 feet, right? A much more compact solution. Now, and Andrew Garcia will take it from here, and he will talk to you guys about the modern current limiting devices.
Yep. Once again, thank you again, Jimmy. Great part of your presentation. Name's Andrew Garcia. I'm the clip system analyst, G&W Electric. Here to talk to you a little bit about these modern current limiting devices and how you can apply them. So once again, just going over before, a lot of the new developments are occurring in the current limiting landscape, driven by the fact that the grid is changing, and a lot of our traditional current limiting devices are being found to be insufficient in a lot of cases. As a result, you're seeing a lot of new advancements continuing to come out, from both faster fault detection, reduced fault durations, and reduced let-through energy. We're going to highlight some technologies that are going to be increasingly common over time. Maybe not something that you would see every day or even most of the time in a lot of wherever you work, but these technologies are going to play a growing factor in the future of the grid. Those are solid state breakers, superconductors, and current limiting protectors. So starting out, solid state breakers. This is a type of breaker that uses semiconductors instead of mechanical components. There are no mechanical components at all in this type of breaker. Because it relies entirely on the electronics, it clears those faults in microseconds instead of milliseconds. That is a fraction of an electrical cycle. That's going to limit the magnitude and duration of the fault almost immediately. Therefore, as a current limiting device. And because it operates and clears so quickly, it's going to virtually eliminate arc flash and fault current from that fault as a result. So that goes in the pros. Fast operation. Once again, clears faults in microseconds. Long lifespan, as it doesn't rely on any mechanical parts, so it can last a longer period of time. Because it's electronic, you also will have enhanced control over the device and when it triggers and what it protects. And once again, it can virtually reduce or eliminate arc flash from your system. However, things often sound too good to be true, and they are, and there are some pretty big cons with these devices as well. The biggest one being that they're very expensive at this point. They're expected to reduce in cost, but they're still going to be a lot more expensive than a traditional circuit breaker. There are limited ratings options currently available. The higher ratings you go, not only are there less available options, but the price and size of these breakers increase pretty dramatically. There's also limited maintenance options for these devices. If something goes wrong inside one of these devices, you could be on the hook for replacing a significant component or portion of these or the entire thing. There's no nuts and bolts in here that you could adjust to try and fix it. When it's busted, it is busted. Another new technology to keep an eye out is superconductors. You're typically going to see these more in the high voltage transmission world, specifically in like long distance DC transmission lines. These are electrical wires made of superconducting materials. Generally, when they're cooled to a low temperature, they have near zero electrical resistance. You can use this as a current limiting device by rapidly increasing that resistance by increasing temperature. That would therefore lower the available fault current by, once again, increasing resistance. However, it's important to note that in order to have this current limiting effect, in order to add enough resistance or impedance to your system, to have that current limiting effect, you do need a very long length of cable. Think in the realm of kilometers or miles. So once again, those pros: zero resistance. That means near zero losses. That can be very valuable, especially in long distance transmission lines. You have very high current density, meaning you can move a very large amount of current. Very large amount of current through a small cable. And ultimately, these are very efficient devices as a result. You can install these on poles that are much smaller than you would argue that you need otherwise. So fraction of the cable size and weight, you end up using smaller poles, ends up being less expensive. But the cons overall is that these are a lot more expensive than an overall regular conductor. Superconductive material is not cheap. These do add cryogenic hazards to your system. That means that your workers are going to have to be trained and equipped to be able to deal with cryogenic hazards, because in order to reach that extremely low temperature, you are going to need pump cryogenic fluid, such as liquid nitrogen, through these conductors. And once again, it does require a significant cable length in order to have any kind of current like that. As a matter of fact, a short run of cable would be said to probably have the opposite effect, and end up increasing the overall amount of fault current by lowering the overall resistance in that conductor path. Next, you have the current limiting protector. This is a type of protective device that uses a pyrotechnic charge to divert current to a current limiting fuse during a fault. It clears faults completely in 1/4 to 1/2 of an electrical cycle. It's a current limiting device, limits the magnitude and duration of the fault. It is the most established of these modern protective devices. It's been around for about 4 decades, but it's finding a wider audience now that the grid is going through these major changes. It's important to note that this is just a copper bus bar under normal operation, meaning that the losses are very low and only becomes a current limiting fuse if a fault is detected. So once again, pros, it's a copper bus bar under normal operation, so it's low resistance. It can go up to much higher ratings than alternatives, magnitude higher continuous current rating relative to current limiting fuse. Goes up to 4,000 or 5,000 amps, depending on that voltage rating. Has a long lifespan, 20 years and additional years beyond that if you follow a maintenance program from the manufacturer. And it is a device that operates in backup, so only triggers in the worst case fault. So unlike something like a fuse or a breaker that can nuisance trip at low level faults, these current limiting protectors are designed to only trigger in response to your worst case 1 in a million fault scenarios to try and avoid those nuisance trip scenarios. So the cons, they are expensive. They are a bit more expensive than an equivalent reactor at the same ratings. However, they are much less in size. They do use pyrotechnics, which is a concern that people have when using these devices. However, the pyrotechnic blast is completely and safely contained within the clip device itself. There's no additional hazard exposed to workers, but that is something to keep in mind. And ultimately, because this is used as a backup device, this is a limited low-level fault protection device. You're not going to be able to use this to clear low-level faults from your system. You need to rely on your regular protective devices in your system in order to accomplish that. So here are some different images and examples of all these different modern current limiting devices. On the left, you have the ABB solid-state breaker. You can see that it almost looks like a monolith. There are no visible mechanical parts and very few buttons to interact with on the front. Basically, there's a designation to let you know whether it's opened or closed, a power button, and some extra buttons for status updates. Top right, you have an example of what a superconductor looks like, which you can see where exactly that cryogenic fluid is going to be pumped through that cable in order to bring that down to a superconductive low resistance state. At the bottom right, you have the G&W's current limiting protector, where you can see inside what's called the G&W interrupter, where the pyrotechnic charges are going to be laid in those notches that are going to be electronically triggered and respond to a specific high-level fault. Once those detonate and that bus bar gets blown apart, copper gets folded back over those larger copper chunks. All that fault current then gets commutated through those current limiting fuses. Those melt and clear. That fault gets completely eliminated 1/4 to 1/2 of the electrical cycle. So how do these stack up against each other? In terms of cost and complexity, your current limiting protectors are going to be the easiest to set up and operate. They're very simple devices. When you get to it, you only have to worry about one setting change. They're much lower cost relative to the other modern devices and can be very cost competitive, especially when accounting for long-term operation costs in regards to things like reactors as well. In terms of complexity, once again, there's not much to say. Once again, there's only one setting with the current limiting protectors. It does require power, but there's no additional cryogenics or additional settings that you need to worry about. Now, in terms of current limiting and arc flash reduction, solid state breakers are obviously going to be your best choice for that, as they're going to be able to completely eliminate that fault in microseconds, which is pretty much as fast as you could possibly go. That's going to virtually eliminate any arc flash current limiting risk. Once again, there are limitations to those breakers, though, that went before. And in second place, current limiting protectors will definitely be there. Once again, it limits that fault in 1/4 to 1/2 an electrical cycle. It's going to completely clear that fault or arc flash event, depending on the scenario. Superconductors come in last just because you would have to run a long length of cable. There's no guarantee just because you increase the resistance to that arc flash or current or fault current event is going to end. In terms of available ratings, superconductors could be said to be the best just because you can apply conductors to just about any system. Current limiting protectors would come in second because they can go up to extremely high ratings, say up to 38 kV, up to 5,000 amps, 120 kA short circuit rating. While solid state breakers are unfortunately at this moment very limited in the kind of ratings they can go to, and once again increase in size and expense pretty dramatically as the ratings increase. However, that's expected to improve as the years go on. In terms of low-level protection, solid state breakers are once again going to be the best. We clear that fault instantly. Superconductors in second, while Current limiting protectors will come in last, as once again, they are not a low-level fault protection device. They're only going to operate and clear that fault in your worst-case fault scenario. So that is a trade-off in order to limit the amount of nuisance tripping from your current limiting device. Last but not least, you have power efficiency. Superconductors are obviously going to be the best for that. You can't beat near zero electrical resistance. Current limiting protectors are once again just a copper bus bar under normal operation, so that's definitely second place. While solid state breakers do incur a small power loss due to all the electronics that are in there. That needs to be accounted for, but it's not significant, but definitely something that you need to think of when you're using them. So going over specifically on the current limiting protector, you can call it CLIP. It is an electronically sensed and triggered device. You do need the electronics in order to trigger those pyrotechnics. Ends up being a fancy copper bus bar without the electronics. It is a fast-acting device, clears that fault in 1/4 to 1/2 an electrical cycle. That being said, it is a single shot device. When those pyrotechnics blow and those fuses in parallel melt, you do need to go in and replace those blue cylinders that you can see on the images to the right. It's a fairly simple process to do so. There's some bolts on both sides of the interrupter you need to take out, some wires you need to detach. You just go and replace the clip, reinstall the wires and hardware, and you go into the control box that's associated with that 3-phase clip unit, and then make sure everything's turned on again. What really makes clip unique relative to other options, what makes it really competitive, it's its high continuous current rating. The ratings that clip can go to up to endurance of current limit can really only be matched by reactors. Think up to 4,000 or 5,000 amps continuous, depending on that voltage rating. By default, they are also both outdoor and indoor rated, meaning that you can install these outdoors without an enclosure behind a fence or pole mounts just by default right off the shelf. They can be installed in an enclosure, both outdoors and indoors as well, with no issue. There are medium voltage and low voltage options. Medium voltage goes up to 38 kV, low voltage up to 750 volts. And once again, just emphasizing that when a fault does occur, all that fault energy and all that pyrotechnic energy is going to be completely and safely contained within those blue cylinders. There are going to be no exposure to hazards such as shrapnel or ionized gases. All of it is completely safely contained. The only additional hazard that you would experience is the sound of a loud noise like a small caliber rifle going off. But working in the electrical area, you're probably already going to be equipped for dealing with noises like that. So shouldn't be too much of an issue. So what are some practical applications they can get into with current limiting devices? So just going over the benefits of why you would use these. You can use lower rated equipment by lowering the available fault current. You can use lower rated equipment, save some money, or keep your project on track if you find out currents are higher than expected. If you have an already existing facility, you could safely operate any equipment that you find is overdutied for a longer period of time without some kind of expensive retrofit. You can end up paralleling sources in your system to increase your available capacity or your reliability of the system without needing a big system upgrade to accommodate that extra fault current. You can reduce overall arc flash risks by reducing both the time to clear and the available fault current. You can eliminate power quality and power efficiency issues from using current limiting reactors, or you could decrease those issues by being able to use a lower impedance transformer. You could also just retrofit an existing system without needing to upgrade your infrastructure. You can use the same pads, the same building, without needing to do a big, expensive upgrade to all those facilities. So what are some best practices for using these devices? I always recommend having them spec'd in if possible at the start of the project in an ideal scenario. Worst case, you end up not needing them, you end up saving money. Best case scenario, you just anticipated the customer's problem, just kept the project on time. It's also very important to pay attention to sources of downstream inrush current. Inrush of current of large electrical devices such as transformers, capacitor banks, motors, etc. Can often be large enough to trigger a current limiting device. So that is something that needs to be kept in mind. Make sure that your devices are coordinated to minimize the risk of that happening. You really want to make sure you can key in and understand user requirements as well. You want a current limiting fuse, but want to avoid downtime. Maybe you should consider using a reactor or current limiting protector instead. Devices that are going to passively continuously operate, therefore no downtime. or a device that's electronically sensed and activated like a clip, that's only going to go off in your worst case fault scenario when you absolutely have to. Those would both decrease your risk and chances of downtime. Say they want to use a reactor, but are worried about the power quality issues. Might be worth then investigating using a solid state breaker, current limiting fuse, or current limiting protector as a result. All devices that are going to avoid that added impedance that a reactor would add to your system and cause those power quality issues. They have limited space, but they want that current limiting device. You want to steer them towards using a current limiting protector, current limiting fuse instead. They might be worried about it having any kind of downtime at all. In that case, your best option would be a current limiting reactor, because once again, it passively continuously operates, and there's no risk of that, going down unless something's wrong with the reactor itself. So how do you coordinate these devices, these current limiting devices, with other protected devices in your system? You want to ensure that these devices are only tripping and being used when absolutely necessary. AKA, you want to minimize the probability that these devices will trip, when otherwise your regular protected devices in your system can handle the fault. Just increase your overall system reliability. So you want to make sure that when you're selecting these devices in the scope of your project, they have the most ideal TCC curve possible, either through modifying those device settings or just overall selecting whatever device like the fuse with the most ideal TCC curve. And if you are using a device that operates passively like a reactor, just make sure to follow whatever pertinent regulations there are. And once again, very important, make sure to account for inrush current. So here's an example of a nuclear power plant where a current limiting solution was used. Here, reactors were used to limit fault current to permit the starting of large pump motors. Their equipment that was in charge of starting these large pump motors was underrated. However, when they used these reactors, they found out they incurred a pretty significant power quality issue, which could affect the long-term reliability of these and efficiency of these pumps. So as a result, they ended up using the clips, which is a lower impedance device than the reactor, to bypass around that reactor in order to avoid that voltage drop. So not only did that avoid that voltage drop, but it also mitigated a lot of that power efficiency loss from the added impedance and saved that nuclear power plant a significant sum of money as well. So here's an example of one line of how it looked like. And the source under normal previous operation would just go through the reactor to the downstream pump motor feeders. That would obviously incur the power quality issue if that were to occur. So what they did was they bypassed that using the clip. And under normal operation with a clip and reactor in parallel, what's going to happen is that current's going to choose the path of least resistance, which is through the clip, and avoid incurring any kind of power loss or power quality issues from the added impedance of that reactor. However, if the clip were to trigger and open, then all of that fault current would then go through that current limiting reactor instead, which would ensure that there's no downtime. However, in that scenario, they would start incurring those power efficiency and power quality issues. So it's an interesting solution called the reactor bypass that I've seen a couple times in the past. Here's another example of a wind farm where clips were used to protect about 121 wind turbines from the grid. They found out most of the way through a project, their utility suddenly reached out to them, let them know that there was a lot more fault current that was available than was previously disclosed to them. It ended up that a lot of their turbines ended up being underrated. They found out that they wouldn't be able to actually energize their equipment and go online without using some kind of current limiting device. They ended up figuring out that clips were the best solution for them, which they then integrated in their system. They were able to energize the project on time and get going. So here's exactly how that would look like. Pretty simple setup. You have your over duty scenario, say 45K fault current available, downstream equipment's only rated for 40K. Then you could put a current limiting device such as a clip in there. It could be any current limiting device. You could summon a reactor or appropriately sized solid state breaker or fuse in there to intercept that fault current and limit it to below that 40K level. Another scenario where I've seen current limiting protector or current limiting devices used is at a major US college campus, where current limiting protectors or clips were used to isolate the cogen system from the utility grid during earthquake. And without the extra protection for the clip, the system could be underrated and dangerous. There's exactly what that would look like. You have the cogen system to be tied into the overall grid at a university, where the added fault current from that generator was adding in a lot of fault current that could bring the system past its ratings. They added a clip into that system, specifically at a tiebreaker or at the generator, to be able to intercept that fault current and bring it below the ratings of that device, such that they were able to operate the system appropriately. So, in conclusion, going over some future trends that I anticipate to see is that these current limiting devices are going to continue to evolve. They're going to limit magnitude to a greater extent. They're going to limit time to a greater extent. You're going to see them used a lot more extensively as the grid evolves. You're going to see traditional and these modern devices to be used. Superconductors, solid state breakers, and current limiting protectors become more common. You may not see them all off depending on what part of the grid you work on, but generally speaking, they are going to become much more common as time goes. So going over what I hope some key points and takeaways you took from this presentation so that you understand how the grid is changing, all these different new sources of energy and new industry that's being added to the grid, the importance of current limitation in managing these grid changes, going over some examples of these traditional and modern current limiting devices and how their pros and cons and how you would implement these in a given electrical system to solve a fault current or arc flash issue, and some real world examples of how exactly that these are applied to kind of take all of these lessons home to see how you would be able to implement this in one of your systems. Any questions? I'll get to go. Jimmy, you got anything to add?
No, I'll echo what you said. You know, these you're gonna start seeing these more and more prevalent due to the changes in the grid, due to the incremental fault levels that you guys are gonna be experiencing in your projects. So that's why now you're gonna see all the solutions that we provided, and hopefully, you know, we'll be hearing from you guys on our solution.
Right. Okay, great. Good presentation. Yeah, I have some questions here for you. For large scale renewables like wind farms, how scalable is this technology? And what are the key design considerations that that utilities have to consider for these multi-turbine applications in terms of protection?
Well, the first one, this is an inherently scalable device. It goes up to very high ratings, so it can be placed in a higher level in the system. So you only need so many of these to actively protect your entire system. They only needed like say half a dozen clips in order to fully protect their 121 turbines from the grid. So it's very easy to scale up on the system. That's often why we recommend people speccing these in earlier, to be able to protect the grid or protect their systems. In terms of, could you repeat the second part of that question?
What are the key design considerations for multi-turbine applications?
It would be understanding a lot of the fault current that's available in that area. Once again, if that equipment inside that turbine is underrated, you have very few options in order to change it without somehow changing the fault current that's being to protect that turbine from the grid. If something were to happen, you'd have to use something like a clip or a current limiting fuse or a reactor in order to mitigate that fault current risk, as there's a limited amount of space inside those turbines, and if that electrical equipment is underrated, once again, you have very few options.
So I'll add that, yeah, obviously real estate, but then the key considerations you're gonna have to, for all the solutions, you have to consider their voltage, the continuous current, and the fault levels. So you're gonna have to be looking at your power study for your fault levers, so you can consider what the capacity of the solution needs to be. On the scalability piece, I'll say that the solutions are, well, I'll talk about our solution is fully scalable. Now there's pros and cons, like Andrew was suggesting. Yeah, on that particular application, they only needed 6 clips. Depending on how or where you place them. If you put them more downstream, then you're probably going to need more. And there's pros and cons for every application, right? You at a lower level, you're probably going to need more units to protect your system.
Okay, thanks. Next question. You talked about how clip integrates with existing protection. Can you elaborate on how it integrates with systems already using fuses and reactors?
Oh, that's a good question. Once again, the clip is electronically sensed and triggered device, so it can be programmed to only go off, to only trigger in response to very high levels of fault current. So you can take a look at, say, your fuses in the system, understand when those devices are expected to trigger, and make sure the clip is set at to go off at a current that's higher than the fuse would respond to.
And he also mentioned reactors. So Andrew gave an application for the bypass reactor. So it's like good complement to the clip, right? During normal operation, the continuous current will flow through the clip, and if there's a triggering event, then it'll transfer to your reactor, avoiding any downtime.
Okay. Next one. What are the maintenance and life cycle implications of using these devices?
Maintenance and lifestyle.
What are the maintenance and lifestyle implications of using these trigger clip devices compared to solid state breakers?
Compared to solid state breakers?
Yeah.
Well, they both need to be continuously tested. The clip itself only needs to be tested every couple of years as part of a regular maintenance cycle. It's pretty simple tests. Their rated lifespan for about 20 years. After that, they can be extended to go through a maintenance program from the manufacturer. Relative to solid state breakers, once again, you'd need to go through test that using the manufacturer's supplied equipment. There's no real set ratings for how long these devices would last at this point, but in terms of testing, I imagine they're both similar. You simulate a primary fault on your system, use like a primary, you primary inject current into the system and determine whether or not the device responds appropriately or not.
I think about the cycle and specifically, I think Andrew answered, right? So similar to when your breakers, so every 2 to 3 years, you'll have to do maintenance.